Those know me, obligatory selfie with my thing that's called a camera. You might not, it's ancient. So, well, smile. So today, I guess I'm coming here to talk about a scheduler's scorecard. Does this work? Yes. So what do I mean by a scheduler scorecard? Well, ideally, what I'm trying to do is rate the characteristics of a scheduler. Not really the scheduler itself. So I'm like looking at what do I want to rate? Things like, how often does the scheduler migrate? Because different algorithms do different things differently. In fact, sometimes we try to keep things on the same core, but sometimes maybe that's not the best thing to do. I mean, we have these huge, L3 caches, it might not be really, actually some of the benchmarks we've done, spreading tasks across the cores, bouncing around, like high migration rates actually perform better than trying to keep tasks on the same core, because there really wasn't much of a performance hit by switching tasks between cores. Looking at how long tasks are interrupted, how often is a task switch is happening, not just how many task switch, but looking at tasks, say how long does it run? Does it get preempted often? Is it kind of like the preemptive rate of different tasks? How long they're blocked. That's not really a scheduler thing, but sometimes it's nice for analyzing locking, which is what we care about. Wake up latencies, of course, CPU frequency changes. What I'm not looking for is actually a benchmark for schedulers. So reason why is because there's lots of scheduler benchmarks. A benchmark to me basically measures a load. You have a specific load, you measure it, and you compare different scheduler algorithms to determine, which schedule algorithm works best for that load. But then again, you can have another load that another scheduler will work better for. So the problem with just benchmarks is you're basically writing the algorithm for the load on the benchmark. So that might not always be useful for everyone.
And this is why you need classification stuff.
Yeah. Okay. So, but what benchmarks really don't tell you is why. Why does one scheduling algorithm work better for this workload than another scheduling algorithm? You kind of analyze it, you can kind of guess why, but you can also be wrong. But there's no real good ways to really validate what your guesses are. So the idea is to have something that say, here's the characteristics of these schedulers, and you could then look at the characteristics of the scheduler, like one scheduling algorithm compared to the other one for a specific load, and then you can also rate like how that load, what characteristics of a scheduler makes that load work better. So, for example, something happened the other day, a month ago. Someone, I guess in the Pixel team, decided to try preempt RT. So because they were using a 612 kernel, 612 now has preempt RT, and they enabled it, and it ended up having a 13% performance hit on when they enabled preempt RT. And they asked me why. When I told this to the preempt RT folks, Sebastian and Clark Williams, like, really, only 13%? That's great. We were expecting 30%. So real time is not about real fast. Paul McKinney's given talks about that. So I have this utility. So when I've been thinking about this scheduler scorecard for some time, and I've been playing around with different algorithms. So I have this utility called task eval that's just a really kind of primitive form of recording stuff. And it's based off of a library called libtraceeval, which I have up on my GitHub. And it's very primitive. I don't like it. I don't like the API. So it's not something I'm pushing right now because I don't like it's still too complex to use. But it's kind of inspired on how synthetic events work. If you're familiar, anyone here familiar with synthetic events? So what a synthetic event does, it takes two trace points and it kind of attaches it together. Here's a quick example of how to enable synthetic events for, like, if you care about wake up latency. So if you go into the syskernel tracing directory, you create your synthetic event right here. The first line is wake up lat, You say I'm going to record the process ID, the priority of it, and the time delta, which is the time from when the task was woken up to the time actually scheduled onto the CPU. And then I attach a trigger to the sched wake up event. It's basically using the histogram logic. So I create a histogram that's going to key off of the process ID. So when a wake up happens, it records the process ID of the wake up. And then I can also create a variable in the histogram, which is I'm going to call TS, which is I'm going to take the timestamp counter in microseconds. If you leave off microseconds, it's in nanoseconds by default. So common timestamp.usex will record into the variable the microsecond timestamp. And then I attach a trigger to the sched waking based off of the next process ID. So the process that's scheduling onto the CPU. And I make keys equals next PID there. And then I take the delta from the, which equals, oh, there's a typo in there. I hand typed this. That shouldn't be, that should be a minus sign, not an equal sign. So that should be delta equals $TS minus common. So that basically, and also it should be the opposite way around. It should be common sense. I have it backwards. Common timestamp minus TS. So this was hand typed incorrectly, so that's all wrong. So I make the delta from the current time from the previous time. So don't copy this. And then here it has a trigger for saying on match with sched waking. So what it does is it matches this process ID with the next process ID. So the process ID that woke up compared to the process ID that's scheduling on it, they match. It triggers then it triggers this trace, which means execute the wake up which is the wake up lat synthetic event, pass in the next process ID as the PID, and the next prio for its prio, and then the delta goes into the delta. So basically, delta is just the timestamp. $sign just means that it's a variable. And also, what I did was I created a histogram on top of the sched waking event. Basically, I said, okay, I just want to make a delta. I ignored the process ID and next PID because that's for this example, I didn't really care. But I'm going to break it up into buckets of 100. You could say buckets. I could put in delta dot log 2, which would be a log 2 range. Or if you leave off this, it's like every bucket is a different delta, which could be if you have you want to keep it into buckets or something. Otherwise, it'll overflow the histogram. And then what I did is I just cat this. This is just I kicked it off and just cat the histogram logic, and it shows you here the line that you have, but then it gives you each of the buckets of how many times hit. So this is I'm sure this is like what you used for your P99.
I added one more thing to stop the trace when I was above the latency was above the value.
Yeah.
So just to make sure to catch.
Yeah, you could put another trigger in on the synthetic event. That's if delta is greater, that you go trace off if delta equals that. You can also do snapshot.
Yeah.
Right. So you could do snapshot. So actually, it creates a separate buffer, and every time the delta is among something, it'll swap it. So you can actually keep a trace. You can enable a bunch of other traces, and it'll actually stop when something happens. So you actually go look back and say, why did it hit this delta? And then there's an on max too, which means that it will do a snapshot every time there's a new maximum. So you just let that run for a while and you just get the snapshot of the greatest maximum.
I just put trace off in the code.
What's that?
I just put tracing off in the code.
Some of us don't just go I know you live in you don't work in user space, you just work in the kernel. Some of us have to deal with user space. So like I said, I did task eval and I tried to figure out a way. So it's if you go to my GitHub account and go to libtraceeval, download it, there's a sample and you do make samples. One of the sample programs is task eval. Again, it's still very primitive, so I would like to fix this. But this is the idea of what I'm trying to look for a scheduled scorecard. So this reads a trace.dat file. So usually what I do is I'll record something and enable sched switch and sched wake up, and it will base this information on just those two events. There's things I do want to add, but I'll probably talk about later. So then at the end, it produces statistics on the information it gets from the entire system for each CPU, for each process. Now, I say each process, and that's kind of lie. It just takes if you have two tasks, two processes with the same name, it'll just say, oh, that's a single process. So it's not, I say everything with the same name will be grouped together. And then each individual thread. So when you run it, the first thing it shows you is tells you, okay, in microseconds, how long the CPUs were actually running compared to how long they were idle. We could do different metrics on this easily. Then for every single CPU, it will tell you, again, how long it was actually running in microseconds. What the average is, how long like it ran like it ran a single thing. And then the max time, actually, like how long it was ran before it became idle. So like this, on average, it was just running like 1.4 milliseconds at a time before it went idle. So it would run, go idle, run, go idle, run, go idle. The max time it actually ran, and then it gives you the timestamp. And again, this is very archaic and old because this timestamp is nanoseconds. So it's not consistent. It doesn't do it. So this is the full actual timestamp. It's because I was just lazy, just slapped it in there. The min tells you where it was. The number of times it ran and, without becoming idle. Here's the standard deviation of the time. Then again, it does the same thing for idle. Like how long was it idle? What was the longest time it was idle? In the same time frames. Oops, I forgot I had arrows. Then it does, like I said, per task. So again, it shows you how long the task ran total. It's wake-up latency. So this is the total wake-up latency I had, but then you can see it breaks it down to the average wake-up latency, the max wake-up latency, min, count, standardization. Blocked, this is kind of interesting. Whenever the task schedules out in task uninterruptible, that's what blocks means. It's in task uninterruptible state. It records all the information there. Preempted is when the task is scheduled out in a running state. So that means something else the scheduler has picked it to run something else. So it's scheduled out, and then sleep time is when it's in a interruptible sleep time. So it could still be blocked like on a few texts, but the kernel doesn't care. And then it does it for every single thread as well. So it has the exact same metrics, the thread ID, but it also has the how many times that thread migrated. So if your information on this as well. But this is the kind of idea of some things to measure. And remember I told you that the folks at Pixel ran preempt RT, and I took their data. I said here, run. They're running Geekbench. I don't know if anyone's heard of that. I guess it's something that you have to pay for, though. It's kind of a proprietary benchmark. But anyway, they ran Geekbench, and with and without RT. And I said, hey, run trace command give me the trace.dat file for get switch, get waking. And I got the information from it. And, the runtime, first of all, it showed that, and this is, I guess, the normal runs too. It ran a lot longer. Like it didn't run as long, quite a bit when it was the real time, but ran much longer when without real time. You can see the average was also quite a bit. It ran a lot longer. It seems so. Geekbench didn't get as much CPU at the time. It got preempted more often when real time was enabled. Like I said, especially the max. You can see the max is much, much larger. You can see that it was scheduled in and out much more often on real time than it was on Geekbench. Wake up latency, the average was about the same. Again, the how long it was blocked, it was blocked almost twice as much in real time than it was normal. So this was actually one of the key things, which makes sense because on real time, we switched spin locks into mutexes. So now in the normal, you'll just spin, but on real time, they're actually going to get blocked and there's a much more higher chance that you're going to be blocked. And this actually, when we did further analysis, that's exactly what was happening. It was hitting the spin locks mutexes much more often. And that's actually where the performance was being hit. Preempt time, obviously, again, the tasks were preempted much more often because also another thing about the real-time patch is because spin locks disables preemption. mutexes, the RT mutexes do not. So when a timer goes off, it's much more aggressive, even though we do have the lazy preemption as much, but it still seems to preempt much more often when in real time than it does in without the real time patch. And so I took these values, I added something, this isn't pushed up yet, but on my own local machine, I made it so that the values or the task eval spits all this information out in a CSV file format. So I uploaded it to Google Docs, the spreadsheet, and I went to manually did the spreadsheet and I created these graphs. Ideally, I want this automated. I mean, I guess Gemini to do it, I guess. That's one way. But here you can see, like, like it kind of shows you from a visual, the block, it's because running is so much bigger, but you can still see from a visual that it kind of stands out where the problems are. I'm using this as an example of saying that we have statistics of seeing how the scheduling is working. You can kind of see why the workload works better with one type of scheduler compared to another type of scheduler. This is more about preempting. That doesn't really quite mean scheduling, but it is scheduling. So the point I'm trying to show here is that, even though task eval is still very, very primitive, it still proved to be very useful, which means I want to extend this and I want to figure out, get a better utility. It doesn't have to be task eval. I want something that, could now take look at the characteristics more and then display it more as a graph. And I'm more interested in saying, okay, how often does this scheduler migrate? How often does this scheduler, preempt? Another thing is I'm interested in seeing that I didn't add yet, but I could add is like wake up chains. How often does what's the latency between a wake up chain? If you have a task that wakes up a bunch of other tasks, or you can even measure, Julia asked me about measuring the application itself, like the work. It wouldn't be nice, like what is the characteristic of the workload? So you could run something to analyze the characteristics of a workload and say, oh, this type of scheduler would be good for this workload. So the SchedX folks could just say, hey, plug in this guy for whatever. And that would be like, maybe you're looking at, does the workload do a lot of chain? Like, this guy wakes up this guy, wakes up this guy. The thread pools things, moving work from there, measuring, like tracing how the task behaves or the workload behaves, and then matching it with the scheduler. Now, this is like a tool that, these are ideas that I'm coming. So my question is like, what else can we measure? CPU frequency changes. That's another thing that might be useful to know. Does this help the workload or not? Newman mapping, like is it bouncing around? Is it taking, do cache misses? This is why I'm also working on, I do have patches out that attaches perf counters to tracing events. My specific group, because actually I started that for this project because I'm really interested in every sched switch to do like what's it, like an L3 cache misses.
Yeah, we want that for a lot as well.
So basically, yeah, I'm really interested in knowing like every schedule switch, what was the impact of the cache. So the code is there. It's just now, so I have it functionally working. I just currently don't like the interface. So I'm working on fixing the interface for that work. So it'd be easier. I'm going to probably make it into a trigger. Just like so it's going to be another, instead of doing a stack trace on each event, you can say, hey, show me the perf, like you could go say sched switch, give me these perf event counters every time a sched switch happens, whether or not the sched switch is activated. So you get the perf events at every sched switch. So that's coming up. So this is, and like, information that I'm looking forward to trying to collect. And if anyone else has any ideas or have anything like to help. So that's all I basically had to say.
I was wondering, can we do this online? So I think for me, it's kind of similar to what TimerLab does for the wake up latency, of course. Only wake up latency. TimerLab actually does this, it collects information and does the thing online, which is, I think, nice because you don't need to save like potentially use trace and then
Right. So like I said, the kind of like you do the same thing with synthetic events, and the histograms.
Right.
So you can collect this information as you go. What's a little bit different, well, I guess you could do like time allowed online. The reason why I did this like offline is because I was also interested in how the threads themselves were affected, and I actually was looking at each individual thread, which you kind of need the trace because you have hundreds of threads, and I don't know if you want to keep that in the kernel or whatnot. But yeah, no, it's not mutual exclusive. They actually work together. Yes, I think we should have something online running to give you what makes sense always running. Like a lot of these statistics you can do, but like one of the things that you don't really have, like I said, when you get down to individual threads and stuff, I mean, we do have like sched stats, but I'm not so sure. Do sched stats actually like record like, when a task wakes up, like wake up latencies? I don't think it does that. And even like some of the other things, and maybe we can do cache misses and seeing like that, like number of cache misses. And
that's very useful. Yes.
But yeah, that's something that we could definitely do.
Yeah. So yeah, I'm actually looking forward to something like I started to sketch something similar for some internal usage, which is I was planning to publish, but it's ugly.
Yeah.
So using perf counters, but the thing so I'm essentially generating CPU heat maps with counters,
Yep.
few misses or branch mispredictions, and then looking at the heat maps, I can figure out if a scheduler compared to another is better or worse based on the there's more cache misses. Of course, I can explain. Look, you are using another scheduler, but you're hitting more cache misses because the CPUs are more hot than
Right.
But the thing is, like, everything is based on sampling. Like I'm kind of missing the events part.
Yes.
So I also want to be able to measure not on a periodic basis, but on
That's what this the code. I have the code up there that it triggers the sampling triggers on the events.
Exactly. That's the part that I would be interested to plug into my thing.
And I just realized, okay, so right now, triggers only work on normal real events or synthetic events or K-probe events. Right now, we don't have triggers on ftrace events. Now, ftrace events are internal events, like the function tracer is an ftrace event. The stack trace is an ftrace event. So basically, because you can't enable, they're not normal events where you just say enable, disable. It's usually enabled by something else. What I plan on doing is making triggers on those events. Although I don't know if I want to do a trigger on function tracer. That's that's when it starts like like the stack trace event trigger something that's like then I could do histograms on the perf event. So you actually go to the perf event and say, give me a histogram for the perf event. Then I might be looking at doing that as well. Yes.
Steven, so you mentioned that you are going to read those counters every shed switch. How about those short-living tasks like 10 microseconds, 15? Do we filter them out or?
Wait, what do you mean? So like if it's a short-living task, I mean, no, it'll still read the counter.
Yeah, and then you will have to store them to the memory, right?
Well, okay, so yeah, the
Thing goes to the trace buffer.
it goes into the ring buffer. That's where it goes. It goes into the ftrace ring buffer. It's a trace event. So when it triggers, it reads it and puts it into the ring buffer.
Yeah, but that would be quite heavy, right? If you have, I don't know, 16 counters tracking different those LC.
You cannot have 16 counters. The hardware doesn't have that many.
We have them. We have 16.
So what do you?
Counters?
So what are you talking about? Because are you saying about switching between tasks, like being attached to a task, you mean, or?
Yeah. So if you are going to track those kind of hardware metrics per task.
No. It's okay. So perf has a per task kind of metrics and has per CPU metrics. I only use the per CPU metric.
I see.
So and it gives you it records the raw counter, and it requires user space to do any. It just says, here's a counter. It's going to truncate it to 54 bits because I'm going to keep like 10 bits as the identifier for what that counter is. And then I'm going to say, just take that counter. Then user space is going to have to figure out like the calculation. What's the difference in delta? It's some other application. I originally tried to say, hey, I was only going to print like the delta I tried to do it per task for using the global one, but that turned out to be a horrible nightmare in accounting. In the kernel, I said, screw it, I'll just do raw and let user space handle the rest.
Have you estimate the overhead when you are enabling all the trace?
I did, but the overhead of the
you run, for example, you run the benchmark.
Oh, you mean with the sched switch trace?
The trace.
So the trace events take about 100 nanoseconds each. So every sched switch is 100 nanosecond overhead. the sched wake 100 nanosecond overhead average. So it's
it's just that when I was using all these statistic event to look for the wake up latency, in fact,
the synthetic event has a bit more overhead. So yeah, I have to like fix the synthetic event code.
the percentile was increasing when I was running the trace, probably also because it was opening more windows for racing.
This is why you just built the logic in the code and use trace on.
Typically one interesting use case with the synthetic event is that you can trace only from it, but you can trace only cyclic test and stop the trace only if the cyclic test is above the threshold, which is a bit more difficult to do.
So there's a few hacks for that. I forgot what's the most useful one, but basically put the trace off in a PRCTL or something and have cyclic tests do that when it exceeds the threshold.
I forgot to mention yesterday, but I think you can use timer lat for what you were doing because it does exactly that.
Yeah, maybe I should have
Just
used that.
use it with scheduler.
So yeah, I mean, yeah, timer lat and stuff like that. Like I said, it's just like for me, synthetic events is more like, yes, it's a quick way of getting something up. And then if you're worried about too much overhead, I do have to work on synthetic events requires a lot of the love right now. It needs, I'm slowly cleaning up the code. Yeah, it's
Timer lat. So for the latency tools, you get the trace.
You get the trace, you can stop when like you get at the threshold, you get the stack trace, you get everything. Yeah.
But Peter, did you have a comment?
No, so you're building a whole interpreter for this magic inside of the kernel, right?
Which
To evaluate your expression.
wait, everything's already in the kernel.
Yeah, I know, but it's a whole separate interpreter again.
What do you mean? Like, wait, so this. This thing goes past this way. This thing?
Yeah, for that thing. You build an abstract syntax tree and then evaluate your condition.
Yeah, well, basically, it's just a hash map. It's a histogram. It's just a histogram.
But the triggers, how do you know when you do the trigger?
Right. Like, so it's a function. It's basically a function call. And so basically when this happens, oh, you mean like for the filtering? Like, so if you have a filter, yes, I do have it's compiled down into a little, actually Alviro helped me write it. So it parses it down and he actually almost makes it into a little binary or like a little opcode. And just like it's an array of instructions that says do this, do this, do this. And because of it used to use indirect, like the compares used to be indirect functions, but because of Spectre meltdown integration, that killed the performance. So what I did was I rewrote it, and since there's only so many compare functions, I made it into a switch statement and just put a number in there. So instead of which function to call, it just here's the number, and it calls and just
this little interpreter.
Yeah. So basically, it's an internal interpreter. Yes. Yeah. Okay. Yes, it's an interpreter. To answer your question, but the thing is, it's been there forever. So, you had a question? Yeah.
Yeah, this seems like an idea that's whose time has come. Andre was pushing for this internally. We've also been pushing for it internally at Meta, including asking Gen AI to generate images of scorecard and scheduler. That came out pretty similar to your slide.
I'm
assuming that was AI generated.
What, the very first one?
The picture of the scheduler.
Yes, I just said, hey, make a golf card that says scheduler, scorecard.
Similar prompts, similar results.
Yeah.
But I wanted to come back to this issue about micro benchmarks. So I agree that it seems really good to have kind of vital statistics, the blood pressure, the temperature of the scheduler. But then, as you said, workloads, of course, there's sort of an unbounded set of workloads. But I still feel like micro benchmarks should be part of the story because, I mean, the whole idea of a benchmark suite is when a community standardizes around it, they kind of draw a line around it and say, this is a good enough representative set of benchmarks, whether it's spec or any other benchmark suite that has kind of community buy-in. And getting into schedulers, like I'm coming more from the user space scheduling world where I worked on work stealing, fork join libraries and things like that. There we would often use micro benchmarks like parfib, right, which is basic scheduler overhead measurement that gives you some signal. But why can't we, for schedulers, come up with a set of 10 or so benchmarks that we feel like represent, SchedBench is one, it's essentially one micro benchmark, but why don't we have more agreement about what is a list of 10 to 20 micro benchmarks?
I would argue that there's different workloads that, like I said, it doesn't, you could be really great in these benchmarks, all these benchmarks everyone agreed with, and then your workload, it sucks. One thing is, this is where I gave a talk last year about scheduler governors, because I really believe that the scheduler for servers should be completely different than scheduler for desktop. And what happened was, I know Peter loves this idea. And because
about latency,
so we actually at in Chromebooks, we have a benchmark, which basically is we kick off like Google Meets, like there's a 16 with 16 different ones. There's also a 48 people. So you have all these videos. And it's fun watching the benchmark because they actually have real videos of people like moving around. And then you have like what's called the Google Docs and people typing. And there's actually, so the test actually simulates typing on it. And it measures key press latency. It measures like if you take the mouse and move it from one window to the next, like, the time that the mouse goes over the window, the time it actually reacts to it. So it has, and this is the thing. And we were talking about the scheduler because there was a lot of jank, there was a lot of lag, there's a lot of things, and we are trying to figure out, and then I mentioned about the Mux scheduler, which was written by Khan Kolivas. And we downloaded it. We ported it to the kernel we had, and we ran it. It was the best scheduler for our workload. But if you run this scheduler on any like servers, it sucks. It's like the worst scheduler for server workloads. But for the individual user, this is why I said if we were everything just went like almost double, like performance just was incredible. All our numbers were like, what the hell? And that's when I'm like, what is this scheduler doing differently? And that's when I actually started analyzing. And this is where I said, I want to know the characteristics. This is what brought me up saying, I want to know the characteristics of a scheduler. Why did this perform so much better than everything else? So that was what was my driving point for doing this.
Yeah, I mean, totally agree. I just don't know how to think about whether or not the variance of workloads is sort of infinite and reducible. Like in HPC, you've got 13 dwarves. And so maybe, Chrome in this latency test is one dwarf, but could you get a set of 20?
Well, this is where going with like Julia's point before, it was like having not just measuring, having a scorecard for schedulers, but having a scorecard for workloads and saying what's the characteristic of this workload? Is it very parallel? Sometimes, parallel workloads would do better being migrated probably across than serial.
The point when this all falls apart is when somebody runs two different workloads at the same time.
Yes, and that's where, okay, so when I talked about the scheduler governors, and this is where my focus was, where I said, I broke it up into actually 4 different workloads or environments. You have the server environment, which would be multiple users, multiple tasks. Desktop environment, which is single user, multiple tasks. Phone environment, which is single user, single task. And then basically an embedded environment, no users, just tasks. So those are like kind of like the paradigm that I see differently. Since I'm on Chromebooks, what our focus was, and seems to be the most reaction, is whatever the mouse is on, whatever is in focus, whatever is in front of the screen, in front of the user, that takes priority over everything else. And we found out, we've actually done studies where if you improve whatever's in front of the person's screen, the user's happier with, they report more satisfaction with the product than if you focus on something else. So that makes sense. I mean, one of the big things when I first joined Google, what we had during the benchmarks here, the key press for the Windows when you're doing typing, which is probably a common thing, you're taking notes in a meeting. It was, if there's too many meets going on, the typing was almost a half second. So every time you hit a character, it was almost a half second before and very noticeable and very annoying. And what we found out was that the meets kicked off with like 10,000 threads, and there's only like 2 threads doing the docs, but it was given the same amount of, it was 1 of 10,000. And when we separated and said, okay, break it up into kind of like C groups, saying, okay, the docs has just the 2 threads of docs has the exact same amount of CPU as the 1,000 threads for things, it sped up real quick. Things like that.
Right, but still, if you have a specific set of workloads and you benchmark things, that somebody combines them, then it basically throws away.
That's actually a new workload. So then you have to combine the 2, and then you create, yeah.
And you get,
This sounds like a combinatorial problem.
that's not true.
Yeah. But still, if you could say, if this is the workload you care about, that's what I'm saying. Everyone has a different workload they care about. So you say, here's a workload we care about. You measure that workload, and then you say, okay, what's the best scheduler for that workload?
No, I would kind of adapt to it.
And Peter's just loving these ideas. Any other? Yes.
You had
What?
stats, right? Set of stats.
What's it? Stats?
The task. You have preempted, blocked.
Where the task? Well, yeah. This. Yeah.
In this, preempt means task got preempted uninterruptible, right?
No. Preempted means that it was running.
It was running and interrupt. It got preempted.
Yes. So another task. It's basically on the run queue. Preempted means it wants to run, but it's not running on the CPU.
Is there a way can split this into preemption happened?
That's not accurate.
Was that?
That's not an accurate description. You can be on the run queue wanting to run while not being preempted.
Right. Is there a way?
So wait. So
A task that just got woken up will be put in the run queue. It will want to run, but it's not
well,
preempted.
that goes under wake up time.
Yeah, I know, but I'm just saying what you said is not accurate.
Wait. No, it's saying what right. I'm saying it was running. I should say it was running. I'll add to it. It was running, and then it's not on. But now it wants to run, but it can't. Yes, I separated out wake up. That's the same thing. Yeah. So the really preempt time total, like I should say not preempt, because it's not. I don't consider that really preempted. I consider because preempted means that you're running, then you're stopped, kind of. So to me, I believe that wake up, you're waking up, you want to run, but you can't run because there's something else is on there, and that's what the wake up time is.
So wake up time here is everything from the waking token to the switch.
Correct. So as soon as you're added to the run queue, to the time you actually got onto the CPU.
Isn't it? It's when as soon as you start deciding which run queue. And
Yeah, it depends on where you put your measurement bits. So
Yeah.
ideally, I'd strip out all of SketchStats and all the other crap because we currently have points where we've got 2 or 3 statistics updates for the one event. And it's just insane. So replace everything with trace hooks, just the ones, and then implement SketchStats and all the other stats shit that we have on top of that as a on-demand module. But I've not found a willing victim yet. It's a matter of work.
Well, maybe I'll do that in the next 2 months. Oh, by the way, I'm leaving Google. This is my last week.
With your synthesized events, like between something and something, do you keep the something and something as well, or are they disappear?
Oh, okay. So you're talking about the. So the way this works is, it uses basically so basically it creates a histogram. So you actually could cat and see the events or the recording. So what happens is there's a histogram table that says the key is the PID. And if you can actually cat, and it will show you the normal, this is the histogram output, and you'll see the type of that inside the sketch waking. And what happens is when sketch switch happens, it goes and looks at the histogram of this match on match, it goes look at the sched waking histogram to see if there's a PID that matches next PID, and then it will actually update its own histogram. But then it also, if there's a match, it'll actually trigger the synthetic event. So yes, it's kind of, the information is there. You can actually look at the information of what happened. Is that what you're asking about, or?
I mean, my experience is every time I try to, like, sometimes I need to reduce the set of events because it's making too much overhead or something like that. But whenever I reduce the set of events, I always regret it. And so you're making these very complicated events at runtime. And then you don't, if you regret it, then you have to make another run and you won't be able to.
Right. But the thing is, this is only like this, the next time the PID comes by, like the histogram is the bucket. So, and what we're recording is the timestamp. So the next time that process ID comes in, it hits that bucket, it updates the timestamp. So this timestamp will change for that. This timestamp will change for that PID every time the PID schedule or wakes up. So you won't have the timestamp from previous wake ups. You just always have the last timestamp, and that's where it queries from. But I mean, you could also enable the event. The histograms don't enable the event, so the events are not actually being traced. I mean, the hooks are being triggered, but the recording into the ring buffer is not. But you could enable it too. They're agnostic from each other. Is there another question? Yes.
Coming back to the same question, sorry. Can you split that into kernel preemption versus user space preemption?
Yes, I could. It's actually would be not too hard. Well, the thing is, you have to define. It's only if the user space tool knows that it's a kernel thread, because it's the task eval reads the trace, and if the kernel thread, if there's a way to know that this is actually a kernel thread. Right now, there's really not a great way to know if it's a kernel thread. Even the flag K thread inside the task isn't good enough to know if it's a kernel thread or not. In fact, I think I found a bug or there's someplace in perf or something where, not perf, but there's something else that did code that required it to be a kernel thread. And I'm like, oh, you're missing some other kernel threads because you're not checking all the things.
Yeah, it's turned into a giant mess.
Yeah. So it used to be that if it has its own structure, it's user space, but that's no longer true. Then we had a flag. And
that's never been true.
Well,
because we had the use thing.
Yeah. Well, but no, I thought that was, but if it had its own because I thought you could have or use yeah. But then even what's it called, the IO ring stuff, it doesn't set the PK thread. It doesn't set the K thread flag.
I know.
It's another flag. It's like worker thread or something. It's like, so you have to, there's like all these flags, and that's why I finally created a helper mat that is like kernel thread or something like that, to say it checks all the things that says this is a kernel thread if all these things or one of these things are set.
Ideally, we would go around and fix it so it sets K thread.
Yeah.
All of these things, because having a very difficult expression to determine whether or not something is a K thread sounds ridiculous.
Yeah, I agree. So doing it from user spaces, like you just have to know that it's a K thread. And you can put information like, okay, I only care about these threads or not. Yes.
You mentioned about collecting the chain of waker key events. Do you have an idea what would be the best way to visualize them?
Well,
Perfect is great because you can follow and see.
Yeah. No, I was actually thinking of like, once you see the chain start, like, in the what's it called?
So I have an awk script that generates an X.dot file.
And I think I think it would be better than, so Perfect, obviously, Perfect is great, but it's huge. Like you can only see a short amount of time. So
I've never seen Perfetto, but
sorry?
I've never seen Perfetto.
Right.
I know you mentioned, but so maybe with actually a simple awk.
So right here,
what I'm missing is like, what's the relationship between like the Waker CPU, Wakey CPU? I want to see them in a more compact way.
Yeah, so you can write a simple awk or Python script to generate X.dot files and then view this and then you can get nice graphs.
Yeah. So it would be nice to have sharing some of this.
I could add to this right here. So when it has the thread, this could tell you who it woke up.
Yeah, I mean,
and then it can also say who woke it up.
Yeah,
And then you,
It's easy
and
to
you
get
can draw graphs from that.
what's that?
And you can draw a graph from that.
Yeah, I mean, it'd be so easy to add that. I mean, I could easily just update it and just do that.
If you want like a Jupyter notebook and you ready to write with a Python code to get your plots, then we already have that.
Yeah. I mean, it's easy to get information and somehow extract them. I wish there was a magic way to say, oh, I immediately see the relation. I mean, I immediately see that this scheduler.
Yeah,
is
and I could actually, and then actually I've learned what graph VX or something like that. Like it does what's it, like Autonoma and stuff like that. You actually can make probably a wake up graph using that.
Yeah, maybe
Dot
some
files.
Was it?
Dot files.
Yeah, the dot files. Yeah,
Graphics.
yeah, graphics. Yeah.
Maybe that's the way. I don't know.
Yeah, I can actually do that. And make actually I could have that's what I'll do. I'll write a little program to say, hey, make the wake up chains, and it'll create a dot file that you can then read in it.
I have an awk file that does that.
Okay,
So yeah, that would be nice.
but you do it from a trace.dat file.
Yeah, so the trace.dat to Python thing is very difficult to use.
Okay, I've never used it. That was written by Johannes.
Right.
So-
So if you ask Gemini, it says that you can write Python plugins for trace command, and you have to put them in the .trace command thingy, and
Yeah.
it'll hallucinate a whole infrastructure.
No, actually, you can do that. You actually can do that. I just don't know how. I've never actually. I just took patches.
I couldn't get it to work. So
Yeah.
I had to actually include that Python file that is in trace command repository.
Yeah.
And then use that stuff. But also the interface that presents is really rather awkward to use. So it has the beginnings, but it's.
Yeah, I mean, I don't write Python. I always tell people like I'm afraid of snakes. I prefer oysters.
Yeah, well, so I can't write Python either. I can just read it and fix it. So I get Gemini to write me the Python and then I go fix it.
So
You can try to.
if someone who likes to do Python, and then wants to make it work with trace command, I'll be happy to take more. Like John Johannesburg kind of orphaned it. So it's kind of, I think there's patches to fix it, but I was nervous to take it. So actually, I think even Tajan actually sent me some patches. I still haven't patched. So, but yeah, the dot file for wake up chains, that's something I'd probably do on my way back to London. Anything else? Thank you.
Cute.